Hi everyone, so today we'll be discussing lecture 10, which is focused on capacitors. We'll discuss inductors in lecture 11. So the idea here is that what are capacitors, what are inductors, and how do they behave as circuit elements. And we will then analyze how the circuits behave when we have these circuit elements in there. So basically, a capacitor, similar to a resistor, is a passive circuit element. When we say passive, we mean that its characteristics cannot be changed dynamically as we operate the circuit. So it's constant, it has a fixed capacitance, for example, that is not modified electronically, right? So that's what we refer to as a passive element. It usually consists of two conducting plates of metal. They could be aluminum, they could be gold, they could be anything. But the bottom line is that there are two plates of metal that are conductors, and they basically are used to make the capacitor. Then there is an element of a dielectric element that is between the two plates that basically forms the capacitor. The dielectric element can be air, it could be plastic, it could be paper, it could be mica, or anything else for that matter. And this whole combination forms the capacitor. So when you apply a voltage across a capacitor, then what you have is that you deposit charges on these two plates. So if we go back to this diagram, if we connect this plate to a positive and this plate to negative, what happens is that positive charges accumulate here, negative charges accumulate here, and you basically build energy around the capacitor. The amount of charge that you store on a capacitor is given by Q equal to C times V. V is the voltage that is applied across the plates of the capacitor. Q is the charge, obviously, and C is the capacitance. So basically, the capacity or the potential of the capacitor to be able to store charges. And we'll look at what defines C. So the unit of capacitance is farad, and 1 farad means that you will be able to store 1 coulomb per every volt. That is a very, very large capacitance, 1 farad. Generally speaking, when we deal with capacitors in electronic circuits, we will deal with capacitance in the range of picofarad to microfarad. Now, the capacitance of a capacitor is determined by the geometry of the capacitor. So basically, the larger the surface area or the metal plates that are used, the larger the capacitance. And the closer they are together, again, is the larger the capacitance. So as the plates get further apart from one another, capacitance decreases. And as the plates get smaller, the capacitance decreases. Now, if we actually write that mathematically, the capacitance is given by epsilon times A, the surface area of the metals, divided by the distance between the metals. Epsilon is the dielectric constant of the material that you use between the two plates. So you could use different materials that potentially will give you a higher capacitance. Now, the most common type of capacitor is capacitors that are film capacitors. So basically, these are very common to see, and I will probably show a picture of one in class, but they are rolled up, they look like a cylinder, and basically there's either mica, polyester, or some other form of dielectric between them. There are other forms of capacitors too, and they are variable, some of them, which are then used to be tuned mechanically by either a human or the individual that is using them, or some other mechanical device that is connected to power. And these are used to, for example, tune radios and other devices. So, for example, the radio knob that used to exist, and now most radios are digital, was basically a variable capacitor that you know one would tune by changing the capacitance, and we'll discuss this in more details. So what are the application of capacitors? Capacitors are very good at blocking DC signals, and we'll look at this very soon. They're very good at passing AC signals. So basically, capacitors make very good high-pass filters. They can be used to create that phase shift that we discussed, or the delay in the cycles. They can be used to store energy, and for example, in renewable energy sources, there are discussions of, or even prototypes of very large capacitors that can be used to store energy. They can be used to suppress noise, again, mainly DC noise probably. And they can also be used to start motors. So for example, a lot of the air conditioning compressors that are sitting outside the homes, they are equipped with a large capacitor that is used to start the motor at the point of starting. And so a lot of times when the compressor doesn't work, it's actually the capacitor that has failed, and it's an easy, very cheap fix. But what is important for us is to always find that current voltage relationship. And if we go back that Q equals CV, if we take the derivative of both sides, what we have is dQ dt, which is equal to I, is equal to C dV dt. So that's the expression that is very important for us. I is equal to C dV dt. And so that's the relationship that capacitors have in terms of current and voltage. We can obviously reverse that and take the integral of both sides and find a relationship between voltage and the current and the initial voltage. Now, the power of a capacitor is given by V times I, as before we mentioned, but I is given by C dV dt. So if we put this in place, we see that the power is given by C V dV dt. If we take the integral of both sides, we arrive at energy, which is given by half CV squared. So that's easily derived. So the energy that is stored in a capacitor is given by half CV squared. So what are the characteristics of capacitors? We're going to assume ideal capacitors. What that means is that there are certain conditions that are met. Basically, the capacitor has, the ability, when you store it with charges, it doesn't dissipate the charges. That's an ideal capacitor. But what is important is that when the voltage across a capacitor is not changing, it basically doesn't allow any current to go through. So when you connect the capacitor to the power supply, it allows a very large amount of current to pass through it. But after it charges, it basically becomes an open switch. So capacitors, if you are constantly changing or turning the switch, or changing the polarity across the plates, changing the frequency, if you have low frequencies, they will not let that go through. But if you have high frequencies, then they basically become a closed circuit and they will let that to go through. So what's important is that if you apply DC across the terminals of a capacitor, it's like an open switch. It doesn't allow any current to go through. But if you actually try to switch the voltages between the two plates very quickly, so if you provide a sine wave to it that has a very high frequency change, then the capacitor is like a closed circuit and it allows the maximum current to go through. So in that sense, they can act as a high-pass filter in terms of their design. So, as I said, an ideal capacitor does not dissipate energy. So if you charge a capacitor that is ideal, you come back a year later, that charge is still there. That's not true in the capacitors. And real capacitors, obviously, the charge dissipates in a sense. What happens is that charges move from one plate to another, so eventually the charges in the capacitor will dissipate to zero. However, we don't really need to worry about that because usually the resistance of a capacitor is very large, so we don't see this happening quickly enough to be important for us. But what's important is what happens when you connect capacitors in parallel or series. So let's connect a bunch of capacitors in parallel. What we see is that overall all of them are seeing the same voltage. So the overall, if we apply KCL at node number 1, what we have is I is equal to I1 plus I2 plus I3 all the way to IN. But we also know that I's are given by C1 dV dt, C2 dV dt, and we could do that. And we take out the dV dt, what we have that is I is given by the sum of all the capacitances times dV dt. So basically that is also given by the equivalent capacitance times dV dt. So now we know that if you connect capacitors in parallel, what you have is that the sum of the equivalent capacitance is equal to the sum of the capacitances. If you put them in series, what we have is that the current going through all of them is the same, but the voltage across all the capacitors is given by the sum of all the voltages. If you again rewrite this as the sum of all the integrals, what you notice is that the overall equivalent capacitance is given by 1 over CEQ is equal to 1 over C1 plus 1 over C2 plus 1 over C3 all the way to 1 over Cn. And so this again straightforwardly follows from replacing that V1 with its equivalent expression, which is 1 over C1, the integral of I t dt. So it's exactly the opposite of resistors. So when you put capacitors in parallel, the equivalent capacitance is equal to the sum of the capacitances. When you put them in series, it again follows the same expression as what we had for parallel resistors. But another way to think about this is that when you have capacitors in parallel, it appears as though you have actually increased the overall capacitance by increasing the area of the plates. And when you put capacitors in series, it appears as though you've increased the spacing between the plates. And so this is exactly what's happening here. We will solve some more problems in class to address some of the issues better. Thank you very much.